Hey everyone, welcome back to my channel. This is day 3 of DSA Bootcamp. I will be starting with GFG portal. As you can see here, today date is 10th July and problem of the day I will be solving. And this question is asked in Amazon and Samsung. Largest square formed in a matrix. If I click on this, it will be redirecting to this. And yeah, I will be solving this here in my notes, in my notepad. Uh, Let me first of all, for example, this question is given to your in your online assessment, and you have to ask to the interview follow-up questions. First of all, we need to understand the question, and based on the question, if you have, you should ask the constraints, and you should ask the maximum constraints first of all, and you should ask for whether we can manipulate the input matrix or not. As an industry standard, we should not tamper any uh, given matrix, given data. You should use an extra additional space to work on your solutions so that the original solution should not be impacted, and it will be helpful for the auditing purposes for the client. Yeah, this is the given binary matrix. Binary means 0 and 1, 0 and 1, and which is the size of n into m, which is kind of a two-dimensional array. You can see that, and find the maximum length of the side uh, of a square submatrix with all ones, which means that you have to find the length of the maximum length of the square matrix which consists of all ones. See, as you can see, all ones are there and maximum length is 3. At any cost, you can see 3. That means that it should be a square. Here, as per the diagram, they gave more space to the length and short space for the width. But if you increase the same length, you can see it was a square form only. Doesn't matter because on length we are getting 3 and breadth we are getting 3. It's a square. So that we have to find the square every time. Square maximum length of this maximum length of the square submatrix we have to find. Okay. For the given input, this is sample test case one, 6, n equal to 6, m equal to 5. Here given one matrix of 1, 2, 3, 4, 5, 6, 6 rows. N indicates the rows and M indicates the columns. Okay, and the given matrix as it is visually displayed, and we have to find out the maximum length of the submatrix, square submatrix having all contains one. We can see that all are contains one. That is what, and we have to return the length, any one of the side. It's square, right? Any length is fine. Okay. For the problem two, all are one. So you can see that at any cost, at any visualization, you will see all are ones and which consists of maximum length of 2. That's fine. And here there is no one, so that we can return 0. This is the edge case. Yeah, and this fine. And time complexity is n into m, space complexity is n into m, and the constraints are 500, 500. If you multiply 500 into 500, 2500, which is possible to evaluate in the runtime in the server within the constant within a second. And the binary, right? So it consists of 0 and 1, so no, nothing else. That's a pretty straightforward question. Hope you understand the question. Let's go to the how we can identify the problem, how we can choose a particular algorithm. If you choose a greedy approach, for example, this is a matrix, right? If you choose finding out, you'll iterate throughout the rows, and then you'll iterate throughout the columns, M into N, and you will check for the consecutive ones. Like for example, here you can see 1 1, and later on, if there is, if you see it was 0, then you can break the column loop, and you can start from the another row. And once you got the 0, you can break that. But it doesn't work out because you are iterating for loop row into column, and also for inside loop you are checking whether particular column while iterating column whether it exists. If 0 is found, You are breaking that. You are taking three loops, order of n cube, nothing but. So which is not suitable for this solution. And greedy doesn't work out. It will blow up the time while running the larger test cases. So that is not a recommended. What we have to do is that see, I will tell you, when you are running on server, like maximum it will take 10 power uh, 6, 10 power 6 maximum. It will take 10 power 6 or 10 power 8, at max 10 power 8. That is the maximum iterations. Maximum number of it will run in within a second. If it is more than that, it will be blown off. For example, 500 cube. If you multiply 500 cube, right, it will give 10 power 5 threes 25, 5 twos 25, 5 threes 125, 125 into 10 power 2, 2 cube means 8. You are getting 8 zeros. Again, it was completely exhausted. So it doesn't work out n cube solution. So in order to drill down, greedy doesn't work out. You have to use dynamic approach. And this is one of the end you can use auxiliary space, which means that it was two-dimensional additional space using for storing the intermediate sub results for each. While going for a single iteration, you can check all the rightward, downward, and diagonal. Three dimensions if you check, and if you store that particular result in one sub problem, and you can do the following same thing for every element, you can find the one DP matrix which result all the sub results sub problem solutions inside one sub matrix, one two-dimensional matrix, and you can return at the end what was the maximum out of it. You can return that. That's what the future. And yeah, we can start with coding. While doing a DP, right? We can use, first of all, we have to discuss with the interview. We should discuss the recursion problem, and then memoization, and then DP, dynamic program. So we should be. I'm teaching you the recursion. First of all, you have to store one variable. We store the maximum. In Java, you can store int array. You can store in int array, which is nothing but like this int array of one with the capacity of one, and then so that if you pass through the recursions, even the next function calls, it will store in the address itself, because arrays are object space and it will be stored in heap memory. It will be modified even number of time frames, number of stack frames. It will be updated on the basis of address itself, arrays. If you are using any normal variable, it doesn't support in Java. In C++, we can use ampersand, which is nothing but address. It will be tampered on based on the address, which resultants. So you can use any one of those. But whatever the pseudocode, that's pretty straightforward for any languages, Java, Python, C++. Vectors, you can use list, array list, that's fine. And coming to the solution, we should start from 0, 0, as I discussed. Here the sub problem 0, you have to check all the dimensions, but the first problem here itself 0, right? No need to calculate the answer. And we should go for the another one. This is one. Whenever we found one, we should check down, left, right, and take the minimum out of those and store the answer. 1 plus 1. If all are 1, then 1 plus 1. That's what. So I will be checking. This is the base case we need to handle. This is nothing but outer edges. If the particular pointer, current cursor, is going beyond the boundary row, if the row is exceeding the limit boundary, and simply return 0. If the column exceeding the boundary, return 0. Taking taking the right diagonal, right value, which is nothing but a matrix, by calling the recursion function, and going towards the j plus 1. J plus 1 means column. J indicates column and I indicates row. This will travels like this and this will travels like this. Okay, fine. And And yeah, rightwards means j plus 1 we are doing. See, as you can see, right is j plus 1, diagonal is nothing but all are increment j plus 1, I plus 1. That's what we are calling the recursion function. And down means we are checking for the only down row plus 1. You can see I plus 1 down direction and checking whether the current index equal to 1. Where the current position is 1, then we can simply add the answer temporary answer equal to 1 plus minimum of any one of those values. The three results, three combination results of subproblems results, and plus one will store the current answer. And then we are checking, we are always looking for the maximum. As the question states, we should always get the maximum length of it. That's the requirement. So we are taking the maximum among those, all the answers, all the subproblem answers, and we are returning that each subproblem we got this maximum. Basically, right, this recursion how it works. First here it will check and it will go for the downwards, rightwards first, and then diagonal and the down. So it will check here like this. It will go till the end of the loop, and once it's completed, and it will be backtrack the solution, and it will store the fill up the table. That's how the recursion will work. Okay. The function calls until the right exhausted, then only it will goes to the diagonal, and until diagonal exhausted, then it goes to the down. Like that, it will follow, and it will store the answers, and it compute, and it will store the maximum among those. At the end, you can return the maximum because it is storing by address ampersand on based on address. Even number of function call doesn't matter. And same thing we can simulate with the memoization technique, nothing but taking an additional complexity. This doesn't work out if the solution is less than 10, then this will work out. If the length n is 10, then we are doing 10 power 3, right? Three function calls we are doing every time. So 10 power 3, it will work, not more than 10 or 14. If the dot n size is so it will work if n size is 14. If more than that, we should optimize this with the help of memorization, taking an DP. As you can see, this is the DP matrix. Initially, we will be storing -1 because of we haven't solved the subproblem, and passing that particular DP in the method call as a additional argument. Same piece of code I'm using memorization. Same base case, and we are checking whether the current position is computed or not. -1 indicates it's not computed. It's not equal to -1 means it is already computed. Do not try another function call. Please return that value. That's what the this particular condition. And we are checking for the three function calls and same thing. And we are every time we are storing in a DP and the one plus all the function call results sub problem results minimum took among those minimum and add plus one. Why we are adding plus one? So every time we see, for example, here, if you see all right, left, down, I mean right, diagonal down, all are 1, which means 1 plus 1 we can add, which is nothing but this act as a subsquare. Like that, similarly, for everything, we will be storing that. At the end, we will be taking the maximum among those and we are returning. That's what the same. We are returning the maximum, we are storing the maximum, and every time we have to we have to return the current subproblem, and at the final end, we will be returning the maximum. This is the current subproblem answer. Okay, we should return at the current function call. Make sure that this proper need to be addressed. And DPV is nothing but a dynamic program where we are doing mm, uh, in recursion, right? We are doing top-down approach. In DP, we are doing bottom-up approach. Sorry. In DP, right? Same thing. Sorry, I have it's very cold. And the table matrix. Here, the row size and column length, and we are storing in one DP matrix to store all the subproblem results. Initially, we are storing at 0 because we are going from bottom to up. bottom up approach. So DP is bottom up approach, so we have to store 0. And in recursion, right, we are starting from 0, which means that 0 is here and is here. So this is like top down approach. This is recursion and memorization. But bottom up, we have to iteration till the reverse. So row minus 1 towards 0, nothing but row minus 1 to 0. This is how. And similarly for column also. Same thing. We have taken starting to end. We are going starting towards end in the memorization here, end to starting. And same thing, right, left, diagonal, and down. Similarly, the respective position, we should take that result as a temporary and store that. And we are filling the table, nothing but we are filling the table at bottom and towards the initial. We are filling up like this. For example, like this, it will fill an entire matrix. And we are taking all sub-problem results, taking the minimum of the fit, adding the answers, because if everything is 1, the condition here states 1 means take into the consideration, add 1 to it. The previous sub-problem plus 1. Nothing but we are storing the current problem and always take the maximum among those. And at the final, as I said, right, we are going from starting 0 here, and then we are going till the top. In the top, you will always have the maximum among those. In the DP, right, like memorization, instead of returning the maximum, you can return DP of n comma m, because as we are taking n plus 1, uh, the matrix DP of n and dp of m minus 1. That is the answer will be stored in our memorization problem. You can try that also. That text. Please comment that solution whether it's working or not. And then yeah, as I said, it's a bottom up approach, bottom to up. So final answer will be stored at the starting position. That's fine. And coming to the space optimization, this time complexity is n into m, and the space complexity will be you are using additional auxiliary space of two-dimensional array, order of n into m. That's also same as expected. This is working fine. This up to this is fine. If the interview asks if even further you can optimize, then you should propose this solution, because this is bit complicated. And if you are trying for fan companies, highly recommend to go through this solution to impress the interview, and you'll get a good percentage of hike. And yeah, this will be starting from maximum, same as similar to DP, but whatever, right? I will be explaining here. See, every time if you notice that this is the current row, and sorry, this is the previous row. If I'm at the current row, like this one, if I'm at here, the position 1, I will be checking down, right, diagonal, and down, right? So here itself failed, and here itself 1 1. So it doesn't store the value, sub result value. We will get 0. And in order to calculate the previous results, we will always using the current only. We are always looking for the one step at a time. We are not looking for five more. We are not jumping five more steps. We are not jumping five more rows above. No, nothing like that. We are every time we are doing only one step at a time. So if you can store the previous row result, then we can solve with the help of one-dimensional array with two rows, the previous row and the current row, so that our problem will be surprised. That's what the this space optimized solution. Taking the row size and column size, this is the current row, and this is the next row, which will be I will be working on. Same iteration starting from bottom approach only, down to up bottom approach. And every time the current row, right, every time take the current of the right towards, and the next will be the I plus 1. And next, here why we are choosing current and next, that is one more question we will be raising, right? I will be teaching why it will be chosen. If you see the DP approach, every time I indicates the current point. If we are moving for the next row, which is nothing but diagonal. If you are looking for down and diagonal, we are going one step next row. We are checking. So any time at any cost you are looking for I plus one, it simply mean by next. If you are at the current position, I indicates the current position, I plus one will be the next array. So you can simply replace this I to the current and I plus to the next, so that it will be suffice. That's what I have done this. And next, and here also we are checking dp of I plus one and j indicates the down. Down, this is diagonal. This is for the diagonal, this is for the down next row. So that we will get, and every time we will get the one only, and all are one, all three sub results are one. Take the minimum out of those and add one to this and store the current only, current value. As you can see, dp of I indicates the current. Current of j we have to return. We have to store. Okay. Maximum. Take the maximum among those, and else dp of 0. Because why we have to reset, right? If any one of those failing, we have to reset to 0. That's what. And at the end, you can result the maximum among those. And here also you can return the next of 0. And this is the main condition in a space complexity. Every time, right, if you are working on two rows and while moving to the next row, we have to store the previous results to the, we have to copy back. For that, we are using the next row. Before going to the next row, please store the previous result, the current result, into the next row, so that you can work on. That's what I'm saying. And every time you have to do, you have to clone the previous results, so that you can go further. And in Java, right, dot clone method will be there, so that uh, you can shallow copy the entire array. That is the more important. Shallow copy will be done. Sorry, clone, right? Deep copy will be done, which means that new installation, new address will be allocated, not the current one. That's what dot clone. If you use direct normal assigning, address assigning, then it will be like shallow copy. The same address will be pointing. That's do not do. Always use clone method only. It internally does the deep clone. It will create a new address, and then it will assign to the particular point. That's what. And here we are optimizing the space. As you can see, we are taking only the order of n. At order of m, we are taking order of m because m is the column. That's what. Here m, order of m, we are optimizing, and rest all time complexity order of n r square. Same. Yeah, that's all. Yeah, thank you. Please like, say, subscribe.